So the agenda for today is going to look at 5 examples, and then I'm going to cap it off with academic care at the end and just point out how the 5 strategies do and does speak to academic care of our students. A little bit of a start before we go, a little bit of cog science, a little bit of my understanding of learning, and particularly these 2 that I'm interested in, and it's something that I've just newly come across: long-term memory versus working memory. Okay, so a little bit of a fundamental understanding of these 2 are going to help as we go through this. Long-term memory, that's where we store the facts and procedures under the term knowledge. You can see the connections being made there. And one of the key goals in mathematics as a mathematics teacher is to facilitate the rapid, fluid, flexible retrieval of that knowledge without putting additional load on the working memory. Now, the working memory is best thought of as the here and now. It's how the student is interacting with the environment around them. But more important than anything else, the working memory has a finite capacity. So we've got to be very careful about how we operate in our teaching and learning environment, because once that working memory is full, no learning can occur. Okay, so if we look at the diagram, rough diagram here, I view it as the students have 5 matches in their box, in their working memory. And if I'm moving around the room, that's 1. If I'm talking, that's another. If I'm demonstrating, that's another. If I start asking questions, that's another one. So they all impact on the working memory. So we've got to be quite conscious of what we do and how we teach so that we don't overload this working memory. For a little bit more on this, cognitive load theory, Sweller is probably the best person to read on that, and he talks quite at length about cognitive load theory and the limits. So first example I want to do is the only strategy in the whole session today that doesn't deal with maths tools, but it had such a strong impact on my teaching in a maths classroom, I thought it was worth sharing today. It comes from a book by Craig Barton, How I Wish I'd Taught Maths. Honestly, if you're a maths teacher, have a read. So here's the example. Here's the strategy. So I'm introducing a new learning episode, and I'm using a template in OneNote, which I'll demonstrate in a minute. The way I do it is I will just work the example in silence. At the end, I pause. I'm then narrating over the top of the example. There are 2 key reasons for that. There are these 2 areas: split attention effect and redundancy effect are 2 things I'm very, very conscious of. Okay, and I want to minimize. The split attention occurs when students split their attention between multiple sources of information, and that results in extraneous cognitive load and impacts on the working memory. Okay, as I mentioned earlier, watching me write, listening to me, moving around the classroom, questions and answers. The second thing is the redundancy effect on students. It's when they're presented with additional information. It's like when I go off on a tangent mid-example. Okay, that is very difficult for students to ignore, and that is also being processed by the working memory, and I want to reduce that. So that's the technique there. Now, once we've got that far, we've done that, I've presented it, narrated it, using class notebook distribute page, or simply letting the students copy, they'll take that template into the class notes area. And so that's the first part. The second part now, it's like in 2 stages. The students will now try what's called a paired problem. And that's when I'm walking around the room off the whiteboard and I'm doing what I call my check for understanding. I'm watching them, looking at them, helping, assisting. This is very early in the learning episode, so that the procedures are not familiar to the students. I do all of this before they go off and purposely practice carefully chosen questions. And the reason for that is if I'm going to ask them to go and practice this procedure, I want to make sure they're practicing correctly. I used to believe practice made perfect, but Barton highlights the fact that practice makes permanent. So we need to ensure that the students are practicing correctly. So let's have a look at how that looks like in my classroom. So here's the template, and it's the same template pushed out across all my maths classes. Objectives, criteria, instruction, that would be my teaching material for the day. And then this is me. Okay, I work through my example, I then narrate the example. It's usually at this point people ask me, says, well, Steve, why don't you let the students ask questions and discuss it as you're going? Look, Q&A is actually quite cognitively demanding for the students, and we want as much of their limited working memory directed towards the new learning episode. Okay, so the students have done that, and now it's what I call their turn. Similar question, similar procedure, similar steps. So they jump away and they have a go. And here's what one of my students, Abby, it is. And so there's Abby. We use digital linking an awful lot in maths. So there's Abby. I've moved around the class. I've had a look at what Abby's been doing and the rest of the girls and said, right, Abby, good to go here. Move on to your learning activities. Okay. She's got the basic procedures in place there. So that is simply just using a template, using digital link and using the distribute page in class OneNote, leveraging those very nicely. Okay. And you can see it's just a standard template, which I push out each and every time. Okay. Now, second one, and this one I had to learn a lot, relearn a few ideas here. I used to not value work examples. Okay, this follows quite nicely on to strategy 1, and also this introduces the first idea of maths tools. I never used a lot of work examples. My philosophy was always that students should be doing maths. Here's the problem, get stuck in, get to work, do it. And I just thought that was logical. There was more benefits than that. However, again, now that I'm getting a greater understanding on this cognitive load theory and the working memory, studying a work example actually reduces the burden, simply because by following through a work example, the student only needs to comprehend, not discover. Now, we've got to remember where we are. We're early in the learning episode. Okay, so the work example effect, the student doesn't have to discover the example, just comprehend it. Okay. And it allows the students to focus on the specific steps to solving problems, and it reduces the cognitive load on their working memory. And that's really, really important. Let's have a look where maths tools supports us in that. We'll jump into statistics. Now I've inked, or you could type, totally up to you how you want to operate, depending on what you've got available. Okay, so let's do some statistics, mean, mode, median, early school years. We use the lasso tool there. We capture the numbers. We go up to the maths tool, select an action, and we got mean, median, and mode. Now we look at the mean. Great, there's the answer, which is good, but the back of the book will do that. Where maths tools helps us here pedagogically is we can look at the steps. Okay, and there's the work example. Now, whether the student got that answer or did not get that answer, they've got an example here of a work example. Also important for us, we've got the assistive technology built in. We have immersive reader there to assist students as well. Now, formatively, students do struggle with the difference between mean, mode, median. And it's sometimes advantageous for them to have these work examples explaining the procedures. Now, this is what we're trying to get into the long-term memory, and we want this to be fluent in future. Okay, calculating a mean, mode, median is something that I would consider a fluent skill my students should have. And again, you can do that for the mode. So this gives the students that opportunity using the work example there to see what's going on. Now, if you don't have a stylus, you can still type the numbers in, highlight the numbers, maths tool, select an action, boom, it works exactly the same way. But we use our stylus. Solving an equation, algebra, always fun. Again, lasso the tool around there, up to the tool, select the action we're solving. Again, answer immediately, that's fine. For a work example, I'm more interested in this. So it gives the student a reference point to look at the steps involved. Okay, they might not be sure, so they look at the procedures, they mimic, they reverse engineer. Okay, it provides them that opportunity there to look at that. It deals with brackets nicely. Higher order equation there, slightly more difficult with the parenthesis or the brackets in there. Same procedure, solving for X, show the steps. There we have. We need to make sure the students are aware of this. Okay, that we point this out, we give them an opportunity, we give them resources where they can go to exercise this idea of a worked example. And again, the immersive reader built in right there. So that's a strategy that I'm starting to use a lot more, and I'm starting to value an awful lot more. Okay, because it's important that my students start to learn to recognize the necessary steps for a particular procedure. Now, strategy 3, independent practice. Now, as maths teachers, we should be familiar with this and comfortable with this as an idea, but it's something Rosenshine pushes very, very strongly. Okay, there are certain analytical facts and procedures in mathematics that we need our students to be fluent in order to reduce the stress on the working memory. Okay, if they're battling to remember, if I take number facts, for example, the girls are working on a particular question and they're struggling to recall 4 sevens. That's going to diminish their ability to do some higher order thinking in the question at hand because they're not fluent in their facts. They're loading up their working memory. They're stressing it. Rosenshine calls it overlearning. And he says it's to become fluent and automatic in the skill, the material almost needs to be overlearned. And he keeps featuring this idea of recalling automatically. Okay, and this is supported here, what I just said previously with the working memory. Okay, if that's automatic, if they're not burning those matches, recalling from their long-term memory, then they can spend greater time dealing with the problem at hand. Okay, metacognition is important at this stage for independent practice. Okay, students knowing what they know, knowing what they don't know, and how to close the gap. And for this independent practice, a great tool exists in Maths Tools to assist us here. Again, you'll see the options here. We're going to solve, solution. We could see the steps. Okay, the student can pull the steps down and have a look at it. But what I'm actually interested in for this particular strategy, independent practice, is the student's ability to generate a quiz or further questions. I usually ask my students, at what level of confidence did they experience solving that question? Now, if it's down at 5 or 6 out of 10, good, we need more practice. We need more fluency at this. So the student clicks on the button down here. AI recognizes the type of equation. It generates the quiz and drops it in their OneNote. If I just close that for a moment, here it comes now. And there's 3 questions of a similar nature, unknown on both sides of the equality sign, and the student can practice them. And if I keep going back to what Rosenshine was saying, overlearning, fluency, automation of set procedures. And this provides us that opportunity there using Maths Tools. Okay, we can extend the idea to expanding. Again, lasso it or type it over here. Oh, now, glad that's happened. Didn't recognize my X, just to show you how easy this is to fix. Didn't like the X I put there, so I very quickly can change that. Boom, that's nice. Select the action, we're going to expand. There's a solution. And again, depending on their level of confidence, the student can generate 3, 5, they can change this to any number they like, 10. Okay, and generate the quiz. But again, we're providing them with a platform so that they can engage with that independent practice. Additional review, okay, elaborate their ideas, check their ideas with a worked example, and the goal there is to gain fluency. Factorizing, okay, key skill as they move through their mathematics. Factorizing, there we have the option. There's the response. Look, in previous years, the students would check their answer in the back of the book, right or wrong, end of conversation. That was it. I got it wrong. What did you do after that? I don't know. Now what we've got here is a few tools available to us that allow the students to, depending on their level of confidence, generate additional questions to support their learning. Okay, and this speaks to their self-regulation. Okay, they're in control. It's 8 o'clock at night. They don't have the teacher next to them. They realize they're not feeling super confident with these. Let's have a look at what we can do to assist them. Now, strategy 4, watching my clock here, self-checking correctives. Now, Benjamin Bloom, I think we've all heard of Mr. Bloom, made an assertion that academically successful students regularly follow up on their mistakes. Now you've got to remember, Benjamin Bloom was doing this back in '84. He had no OneNote, no Maths Tools, no quizzes. Okay, but the point is still relevant. Okay, what do the students do? Following on from the previous strategy, what do students do when they find that there's an error in their work or there's a misconception or a gap in their knowledge? What opportunities are we presenting to them in order to engage with the learning? Now, I've done this in the last 18 months, 2 years with my students, and I found this point to be very relevant. Correctives can be new for students, and I learned from an English teacher. I used to tick, cross, give the work back, and she said, well, that's the end of the conversation, Steve. Why do you have to tick and cross? Why can't you circle a concept with a question mark? Continue the conversation. The student goes away, has another try, comes back. Okay, but as soon as you tick it across it and then write the right answer, the end of the conversation, the end of the learning, the student just got it wrong. So what we're trying to suggest here is using aspects of the maths tool to support that self-checking and correctives. Here's a reasonably common question, year 9, year 10 maths. Equation of a linear function, state the gradient of the line and the y-intercept, sketch the graph. Cool. So the students made their attempt, lasso the equation, come over to maths, and we're going to graph it. Boom. Great. Now, some key features I want to see are the zeros and the y-intercept. I'm just going to make that a little bit larger. I can pinch and zoom that. So I've put that on the page. Now, right on top of my work there. So what this is going to allow the student to do is actually compare and contrast. Did they label their graph with the axes? Do their y-intercept and x-intercept agree? Can they see 6, 2? A change of 6 on 2 as it's falling is a gradient of 3. Do they have something as simple as the arrowheads on the graph? So there's that ability to check and recheck and compare and contrast. That's independent of the teacher. Step it up a notch with a quadratic. The reason I'm choosing the quadratic, a few more features available in maths tools. Coming across, again, we've got a little error there, so I'm going to fix it. Doesn't like my X. Here we go. That's looking good. Action, graph it. Okay, now again, I'm going to pinch and zoom because I'm really interested in what's going on here. So what does maths tool tell us about key features? Okay, yes, I want to see the zeros, the y-intercepts, I'm interested in highlighting them, and the critical point there. Good, insert that on my page. So the student can have a look now and say compare and contrast with what they've drawn. One of the most common mistakes my students have here is their intercepts. They might have them round the wrong way. So again, that speaks to a factorising problem. Okay, so again, I might ask them to check their factorising. Got to fix that X. Just check your factorising. Okay, did you get that? That tells you it's 4 and negative 2. Most of the students, if they make the error here, give me x plus 4, x minus 2. Okay, so they can show the steps, they can generate the practice. So we're actually discriminating and isolating where the error is. Okay, we've got the turning point. I like my students to use or demonstrate the axis of symmetry. Here comes the ruler. Bring the ruler across, axis of symmetry goes through the turning point. If I can get my 90 degrees going, there we go. Axis of symmetry straight through the turning point. Okay, and we put that in. Again, checking features, key features, y-intercept, turning point, axis of symmetry. Axis of symmetry is correctly labelled. We've got that happening there. Step it up to my senior students, differentiating, bit of calculus. Differentiate that, maths, differentiate. Okay, we want to see the steps. We've got the answer. Now, straight away, chain rule. Boy, didn't realise it was a chain rule. They might have used the product rule. And again, immersive reader, worked examples. They can work through that and go, there, right there at step 3, I failed to do this properly. Boom, correcting. Okay, not simply looking at the response. That's it, that's what they got there. I did not get that, I'm wrong. They can now take that a little bit further. Okay, last strategy for the day. And this one was interesting for me because it challenged me with students who had higher learning rates. And I fell into the old trap early in my teaching career, which I quickly got out of, is if a student finished early, I rewarded that student by giving them more work to do. So they're smart students, they're just going to keep quiet. Okay, so I had to think about how do I extend, enrich the activity for the students. And again, go to the research. What does it actually mean? Thomas Guskey, brilliant. Okay, and he said, look, if you're going to provide effective activities, they must, 1, be challenging, and B, provide a valuable learning experience. So that's a true enrichment activity. Okay, and look, don't be afraid to go beyond the established curriculum. So they were 3 key points that Guskey pointed out that allowed me to think a little bit more broadly about enrichment and extension. And again, here's where maths tools in OneNote supported this. We do solving monic quadratics at the moment in my year 10 class. And the way we would solve that, take it up to maths tools, fix my x's. I want to do some work on my x's. There we go. Nice. Okay, and we're going to solve. Now, solution. However, maths tools will provide us 4 different methods to solve this. Now, my girls know how to do factorizing, so what I might say is, okay, have a look at completing the square. See if you can look at how they arrived at the same answers. Can you reverse engineer that? Can you see what they've done? One of the things I'm hoping to get out of them there is perfect squares. Okay, they've leveraged the idea of a perfect square to solve that quadratic. But again, many opportunities for the girls to reverse engineer, to have a look at how they did it. This is another one, simultaneous solutions. Notice with the digital linking, the elongated brackets there tells the maths tool that it's actually a system of equations. There we have it. And we're going to solve these simultaneously. Okay, I did it graphically, but let's do it algebraically. And again, 3 options. Myself personally, I'd look at that and go, well, girls, I hope we're going to do that by elimination. But as an option, I could ask the students to examine the steps involved in substitution or go matrices. Now, I wouldn't expect a Year 10 student to fully develop the skills of inverting matrices, but I'd be hoping they'd be able to see the similarities between my system of equations and what's happening on step 2 there, matrix form for the first time. So again, watching my clock here, being very mindful of the time, they're just some examples of where the built-in maths tool allows us to present opportunities to our students to develop their range of skills. And brings me to my final point here, academic care. Okay, metacognition is a key one for me. Okay, getting the students to know what they know what they don't know, and how do I close the gap? I always say to them, look 3 places before you ask me. Did you look at your notes? Did you use maths tools, etc., etc.? And we talk about Dylan William here. He talks about effective learners are self-regulating, but he also makes the important point that we can teach this. Self-regulation can be taught. And improvement in metacognition raises their performance. But it's incumbent on us, if we want these promoted, we've got to give them an opportunity with meaningful learning activities. And that's where I believe maths tools comes in and kicks a great goal for us. Okay, look, that was it. That's right on the 25 minutes mark. What we're going to do now, we're going to go back to the call